So I want to say a little bit about one other famous canonical continuous random variable. Not as famous as the normal random variable by any means, or even as famous as the uniform, but still one that you might encounter. It's the exponential random variable. Okay. Exponential random variable is a random variable we tend to use if what we're trying to model is the time until something happens, time until democracy fails, time until somebody resigns, time until light bulbs burns out. Those kinds of uh, scenarios are things that we would use a exponential random variable for. And the PDF for that exponential random variable, what makes X an exponential random variable is it has this PDF. Lambda times e to the negative lambda x, where lambda is some number that's greater than 0. And what that looks like in terms of a graph, do it for a couple of different values of lambda. So here's one, and here's one. That's a slightly better one than my purple one here. There are these kind of downward sloping, getting flatter type curves. So negative first derivative, positive second derivative, because that negative slope is flattening out here. The intercept for the PDFs are lambda. Okay, so if the purple one here is, I said purple, but I drew blue. Say the blue one here is lambda equals 2. That would be telling us that here the intercept would be 2. And the purple one, lambda equals 1, is telling me that this intercept is 1. And so something you can see here is that the exponential random variable only takes positive values. So if we really wanted to be, I don't know, overly complete, we could say that the PDF is lambda e to the negative x for x greater than 0 and 0 otherwise. But for something where it's kind of like this obvious portion of the real line, we tend to skip that part. Also, if you think about the fact that it's representing the time till something happens, negative time doesn't really make sense here. Okay, so first thing I just want to do is let's make sure that this is valid PDF. So let's just make sure that the integral over the entire sample space, that's from 0 to infinity of lambda e to the negative lambda x with respect to x, make sure that that equals 1. Okay, so let's just do that. First step is to find the antiderivative. Look at this lambda e to the negative lambda x, and just kind of in our heads try to reverse the differentiation process, asking ourselves, well, what kind of function would have a derivative of lambda e to the negative lambda x? I'm going to assert that this function does, negative e to the negative lambda x. Okay, so we're losing the lambda in front there and gaining a negative sign. Let's check whether the derivative of what I'm saying, I'm saying that the derivative of this thing is the PDF. Let's check to make sure. Negative e to the negative x, taking that derivative with respect to x. So the negative sign out in front, that just stays there. I bring down the negative lambda because that is the derivative of the inside function. I'm using the chain rule here. And then the derivative of e to something is e to something. Exponential functions are their own derivatives. So that last step is just e to the lambda x, keeping my x there, and the two negatives cancel out. And yes, so this is the antiderivative of lambda e to the negative lambda x. Hooray. And so then what am I integrating from? I'm integrating from 0 to infinity. And here I'll remind you of something that I think we kind of touched on in math camp, that when we have infinity or negative infinity as one of our limits of integration, we have to take a limit to evaluate it. Okay, so the first part of the definite integral is just the limit as x goes to infinity of negative e x, and then subtracting it off, we have negative e to the negative 0. Okay. Really the only tricky thing here with the exponential functions, or the main tricky thing, is managing all those negative signs. They really pile up here. But yeah, so what I've got is the indefinite integral. Can't evaluate it at infinity, but I can take its limit as x goes to infinity, subtracting off the indefinite integral evaluated at 0 at the lower bound there. Okay. I want to do one more step on this first term before taking the limits, and I'm going to just rewrite it in a way that will help me see what the limit is. Okay, so not taking the limit yet, but what I'm going to do here is I'm going to rewrite that negative e to the negative lambda x is negative 1 over e to the lambda x. Okay, so I'm reminding myself that this negative here in the exponent means that the expression is down here in the denominator of a fraction. Why am I doing that? Because now that I've got it written that way, it's easy for me to see that the limit of this thing as x goes to infinity is 0. Okay, it's easy for me to see that I've got something that's being raised to a higher and higher power as x is going off towards infinity. So that denominator is going off towards infinity. So the whole thing is going to 0. And then, okay, so good, that whole first term goes away. My second term, the two negatives cancel each other out here, this negative and that negative. So I've got plus e to the negative lambda 0. Oh, that's just e to the 0, which is 1. That's what we want. Okay, so yes, this is a valid PDF. Phew. Okay, so now I want to just go through a couple more things about the exponential random variable. And what I'm trying to do is cover the things that for discrete canonical random variables I put in that table. I put the PDF, the CDF, a formula for the expected value, and a formula for the variance. And we've actually gone over that information for the uniform and the normal random variable. I'm going to do it for the exponential random variable too. Okay, so we've got the PDF. For the CDF, so let's just remind ourselves what we do to get the CDF here. What we're going to do, we're going to find f of b, which is the probability that x is less than b, and we're going to find that as the integral from 0 to b of PDF. Okay, fine. We just integrated basically that same function. So the indefinite integral, the antiderivative part, will be the same. Still going to be negative e to the negative lambda x, but now we're going from 0 to b here, and that is going to be negative e to the lambda b minus negative e to the negative 0. This whole term once again turns into a positive 1. Okay, we've got the e to the 0 power, that's 1. The two negatives cancel out. So 1 minus e to the negative b, that is a CDF. Okay, great. And we can use that CDF to calculate cumulative probabilities just as we always do. So let's let's calculate an example. Let's do one of the ones that we did as a integration problem in math camp, and just again sort of being more mindful now of what we're actually finding here. So let's think about the case where lambda is 3/2, and what we're looking for is the probability that x is between 3 and 4. So drawing that picture again, drawing the picture here, and I'm going to draw the PDF. And again, that's one of the things that's tough to manage with continuous random variables, because sometimes we are working with the CDF, sometimes we're working with the PDF. The two things are related. You just got to have your antenna up to remember which one we're talking about. Okay, but here, what I am drawing here is little f, the PDF. Okay, and if lambda equals 3/2, it's telling us that that point is 3/2. And if what we're looking for is the probability that x is between 3 and 4, we're looking for this area. And the way we find it is we take the CDF evaluated at 4 minus the CDF evaluated at 3. Okay, so lots of different ways to think about this. They all get us to the right answer. We could think about the probability that x is between 3 and 4 is the probability that x is less than 4. Oh, that's too big. We have to subtract off the probability that x is less than 3. So the probability that x is less than 4 is this whole area. That is big F at -4. We don't want the whole area, so we subtract off big F of 3, which is the white area that I'm kind of circling around here. And since we just found the CDF, we can just plug those numbers right in. So F of 4 is 1 minus e to the -3/2, okay, because we're thinking about that specific value of lambda, times 4, minus 1 minus e to the -3/2 times 3. And so yeah, so all I've done here is just substitute 4 in for b, and then substitute 3 in, taking the difference. The two ones cancel out here, and this negative cancels out that negative, so I end up with e to the -9/2 minus e to the -12/2. That sounds like e to the -6. Those are numbers, and the difference between those numbers is 0.0086. That is the probability that an exponential random variable with parameter lambda is between 3 and 4. All right. Yeah, so let me say a little bit more about the exponential random variable, this idea that it's a time till something happens. Sometimes people will say it's the continuous analog of the geometric random variable. Okay, so remember, geometric random variable for discrete random variables, we're thinking about Bernoulli trials. Here, it's the number of trials until your first success. So the geometric random variable also has this kind of time until something happens. But for the geometric random variable, we're measuring time in these discrete chunks, which are trials, okay, the number of coin flips. So we're measuring time in terms of coin flips, which is weird, but that is how it works with geometric. With exponential random variables, it's the same kind of idea. It's the time until something happens. Okay, and it is actually, it has the kind of same relationship to the Poisson random variable that the geometric random variable has to the binomial. Okay, so we know the binomial random variable is also based on Bernoulli trials, and it's the number of successes in n trials there. The Poisson random variable has this parameter lambda, and guess what? It is the same lambda as in the exponential random variable. Okay, so if we are thinking of like the events, the sort of the rare events that the Poisson random variable is representing, like let's say that's cabinet resignations, and let's say that there are 2 per year. Okay, the exponential random variable would tell us the amount of time to however many, the amount of time to the first resignation. So let me say that correctly. If what we're thinking about is cabinet resignations, and if we want the number of resignations per year, say it's on average 2, so the Poisson parameter lambda would be 2. The exponential random variable for that same story would tell us the expected number of years to the first resignation. Now you can just kind of think about that in your head and say, well, if we have on average 2 per year, then I expect to wait half a year for the first one. And you know what? You would be exactly right. That is exactly what the expected value, go back to black here, of x is 1 over lambda, okay, for the exponential. And the variance for the exponential is 1 over lambda squared. Okay. So we're going to study the exponential random variable a little bit more in our workshop. It is a nice, simple random variable. It's easy to work with. It's sometimes a little bit too simple for things that we want to represent. That's you're kind of used to that situation now. The thing that you can also see from these claims I just made, I'm not going to derive the expected value and the variance, but I am telling you what they are. As lambda gets larger, both the expected value and the variance of an exponential random variable decrease. Okay.